Okay. Howdy everybody. We're going to be looking at Unit 6, multiple choice questions. There's actually only one set of multiple choice questions in Unit 6. There's no B, so we'll just call this multiple choice question. Okay, so we're going to go ahead and skip the first 6 for now. We're going to jump into question 7, as those questions all rely on they build off of each other. And so the explanations can get a little long-winded, and we'll go ahead and save those for the end here. So here's question 7. We are given a force versus a displacement or position graph, sorry, and it reads, a 4-kilogram cube is placed in a container of water. The student observes that the cube floats and the net force exerted on the cube represents the sum of the force due to gravity and the force exerted on the cube by the water. A force probe is used to measure the net force as a function of the cube's distance from y from the bottom of the container. The graph shows F as a function of y, where y is the positive direction, where the positive direction is upward. Which of the following statements is correct about the motion of the cube if it is released from rest at a vertical position of 0.05 meters? So we'll go ahead and do this poll. Let's see what you guys are thinking. And as usual, if there are any questions that come up, don't be a stranger. All righty. So we'll go ahead and end polling here. So let's go ahead and see what's going on. Well, if we notice, the force is going to change as this object moves in different positions. So for instance, when it is 0.5 meters from the bottom, maybe it's something like this here, and we hopefully know that cube tends to float. So it's going to experience a force that points up. Now, as this cube begins to move upwards, away from the bottom of the container, at some point it feels no force. But that shouldn't automatically indicate that it stops. All it means is that at that instant or at that position, it feels no force. And because it's been experiencing a force for all this displacement, we can think of it as there's work being done on this. This guy is changing its kinetic energy. And this isn't a work question, but we think of all of our tools in our kit and realize, okay, this guy is moving such that if it has a velocity here that it has gained from all this work is force times displacement. So the area of this graph, when it feels no force, all that means is that it's going to continue moving. There's nothing to stop it there. And then once it passes over that point, we notice the force is negative. And so here the net force is pointing in the opposite direction. And if we compare magnitudes, here we're at about a magnitude of about maybe 7-ish newtons. This would be 8, 6, 4, 2. And it's going to feel an approximately equal magnitude over here, about -7 newtons. That means that the net force is down. So even though this is not a spring system, this is going to oscillate. This is a harmonic system. One way we can think about it is we have a force trying to bring us to an equilibrium point. As we go too far upward, as our position gets too high, we start to experience a force bringing us back down. So if we look at this data, right away, this is a gank. The acceleration is not constant, and the reason it's not constant is F, the net force here, is not constant. It varies in magnitude. It gets smaller and smaller and smaller, and then it gets bigger and bigger in magnitude. So not B or A. By this virtue of inertia, it's been moving, it has velocity. It is not going to come to rest the moment we stop pushing. If I'm on a slippery ice track and I'm pushing, that object is getting faster. But the moment I stop pushing, the block doesn't automatically stop. It's friction that stops it. And if there is no friction or opposing forces here, it's not going to stop. It's going to keep its motion. So it's going to overshoot. And now we have a force, a net force in the opposite direction. And in this region, it slows down. Here it's getting faster. And so this is kind of like a buoy or some kind of life preserver on the water. It's going to oscillate for a bit until things damp out, but it's because the force, if you submerge it too far, pushes it up. If it goes too far up, you don't have enough buoyant force. We'll find out in physics too. And so it's going to come back down into the water. And so D is our best answer choice. It's going to oscillate between these 2 points. If we notice, we only have data in this bound, which kind of justifies that. And the other ones were just bad answers. They're taking advantage of like just you thinking the force is zero, this thing stops. They're taking advantage of you seeing a force and thinking the acceleration is constant in magnitude. But we can see from the data that the force is changing in direction, so the magnitude and direction. So the acceleration is going to change in magnitude and direction. Let me know if we have questions on that one. Number 8. A student attaches a 0.6 kilogram block. Oh, sorry, let me pause polling real quick. Sorry. A 0.6 kilogram block to a vertical spring, so that the block spring system will oscillate if the spring is released from rest at a vertical position that is not the system's equilibrium position. We've said this before. They're just telling us that it's going to oscillate. The student measures the velocity of the block as a function of time as the system oscillates, as shown in the graph. Velocity, time. The spring constant of the spring is most nearly, let's see what you guys get. I'll give it about 45 seconds. This one takes a little bit longer. Alrighty. So let's go ahead and see here. The two equations that we know use the spring constant is the force from a spring, which is Hooke's law, and it says that the displacement is proportional to the force, or the force is proportional to the displacement by some constant. And the negative there is just for the direction. If I pull this block to the left, it's going to feel a force to the right, and that negative flips that to fix that. The other equation we have is the period of oscillation for a spring system. This is the Mortal Kombat equation. Now, if we look at these two expressions, we may be wondering, well, which one is going to work best here? Well, we have velocity, we have time. None of these really give us any bit of information. We don't know the force, we don't know the displacement per se, but we do know that this is the time to complete a cycle. One oscillation. So if we look at this, our object starts on the positive side, a distance, with a velocity of 0.5, and it's going to go through its motion. It's going to come to a stop at some apex of its motion, and then it's going to return with a velocity in the negative direction. And so when we're finally done here, one complete cycle of oscillation is going to be when we return to the same position, or when we have the same velocity or the same acceleration. So it looks to me like the period of oscillation, T, is going to be 3 seconds. So let's see here. So looking at this, we get T squared equals 4 pi squared, M over K. All I did was I squared both sides. Oops. We're looking for the spring constant. The spring constant K is going to be given by 4 pi squared. The mass is 0.6, and the period of oscillation is going to be 3 quantity squared. So looking at this right away, how can we get a quick answer? Well, pi squared, and especially Alabama, in Alabama, pi is about 3. They say that it's equivalent to 3. So we can kind of say, okay, these two factors are not going to be far off. Pi squared is about 10, actually. And then we have 4 and 0.6. So we should know that 4 and 6 multiplied is 24, except we have that little decimal here. And so B is our best answer choice, 2.6 newtons per meter. And you could type that into your calculator if you'd like. But I'm just kind of showing you here. If you know your arithmetic, mental math is faster than your fingers. Let me just make sure that we calculate it. Yeah, we're good. All right. Let me know if we have any questions. Question number 9. A student must use an object attached to a string to graphically determine the gravitational field strength near Earth's surface. Okay, let me check the chat real quick. Okay, they try to make it 3.2 in Indiana by law. I mean, oof, that's risky. Anyways, we'll focus on this. Sorry, because I can go on random spiels. The student attaches the free end of the string to the ceiling and pulls the object string system so that the string makes an angle of 5 degrees from the object's vertical hanging position. The student then releases the object from rest and uses a stopwatch to measure the time it takes the object to complete one oscillation. Which of the following is the next step that will allow the student to determine the gravitational field strength? So let's see what we're thinking here. I was like 3.2. I don't think that's a nice clean number. 2.7 is, I think, e to the 1. So in some classes, e to the 1, pi, square root of 10, or square root of g, they're all kind of the same number. And in astronomy, you don't really care. You do order of magnitude approximations. You don't care about those factors. All righty. So let's go ahead and see here. We have learned that the period of oscillation for a pendulum, that's basically what this is given by 2 pi square root of L over G, the Louis-Gasquet equation. So if we look at this, we already know the period of oscillation. They told us that in the beginning. And we're trying to find the, oops, that's supposed to be a highlighter. And we're trying to find the acceleration due to gravity. Gravitational field strength happens to be the same thing as the acceleration due to gravity. So what else do we need? Well, 2 is just a number, pi is just a number. We need the length. Repeat the experiment by adding additional mass. Very important. For a pendulum, the mass does not affect the period of swing. Yes, it feels more force pulling it towards the equilibrium point because it has more weight, but it also has more mass or inertial mass, and those two effects cancel out. Because the more mass you have, the smaller the acceleration. So one is increases proportionately to mass, the other one decreases proportionately to mass. Those two effects cancel out. Repeat the experiment by changing the length of the string. Okay, B looks pretty good. They're mentioning the length. Repeat the experiment by changing the angle. Very important. For simple harmonic motion, where theta is less than about 15 degrees. If you ever see small angles means that theta is going to be about less than 15. Some cases less than 20. It just kind of depends on the thing. But anything less than a big number, and a big number being like anything above 20 in my opinion. But for small angles, the amplitude makes no difference in the period of oscillation. Okay, so this won't really help us out here. We need the length. It really shouldn't change the period of oscillation, but if we pull this greater than 15 degrees, we will start getting a weird effect, and we won't be able to take account for it with these equations. Repeat the experiment, measuring the time it takes to make 2 oscillations, 3 oscillations, 4. Now, this is to minimize experimental uncertainty, and so our best bet here is B. Let's go to number 10. The student attaches a mass of big M to the end of a string of length L so that a pendulum is constructed. Student Y attaches an object of mass big M to a string of length 4L to construct a second pendulum. Which of the following claims correctly compares the period of student X's pendulum to the period of student Y's pendulum. Let's go. All righty. So let's see here. We want to compare the period of student X's pendulum to student Y's. And we've seen that the period is going to be given by some factor 2 pi square root of L over G. And so the main difference is student Y's pendulum is 4 times longer. And there's a 2 pi. So when making these comparisons, the 2 pi's don't matter. We make a ratio, they cancel out. And same thing with G. What we can say is that the period is proportional to the square root of L. And so we can say that Ty is going to be square root of 4L, or 2 times greater than student X. Hopefully we can see this. This is the time for student X, it's square root of L. The other guy is square root of 4L, and the 4 square rooted is a 2. So the period of of student Y's pendulum is going to be twice as big. So C reads pretty good, but this one is saying that the shorter pendulum, student X, is going to take more time to swing. No, the longer the pendulum, the longer it's going to take to swing out. And so these are best answer choice. If you guys were thinking C, you're correct about the square root, but your square root was in the wrong place, or you interpreted that square root incorrectly. And so, well, bam. A sounds kind of like the gotcha. You see that the mass here is the same, and you're thinking, well, the mass is the same. But mass, it only affects a spring mass oscillator. Length affects the pendulum. The spring mass oscillator is just like a mass on a spring, by the way. And let me know if we have any questions. Number 11. The gravitational field strength near Jupiter's surface is nearly 2.53 times greater than the gravitational field strength near Earth's surface. Which of the following claims is correct about the period of a pendulum that oscillates near Jupiter's surface and near Earth's surface? Oh, shoot, I've not been recording, right? Oh, no, yeah, okay, I am recording. I thought I'd forgotten. I forgot for one of my physics 2 sessions. All right, we'll go ahead and call it here. 11 out of 12 responses, very nice. Okay, so let's see here. We have seen that for a pendulum, I keep forgetting to do that. For a pendulum, it is inversely proportional to the acceleration due to gravity. Or we could say that it's proportional to L over G. So maybe we're thinking, hey man, that length depends on the length of the pendulums here, right? And so I saw that D was kind of popular. But if it's the same pendulum, and it makes it seem like that because about the period of a pendulum, if it oscillates near Earth's Jupiter and it oscillates near Earth's surface. So we don't really care about the length here because it's going to be the same pendulum in both cases. And so we see that the period of oscillation is inversely proportional to G, the gravitational field strength. So the bigger the gravitational field strength, the smaller the time. So maybe we're thinking the period of the pendulum will be greater on Jupiter. The acceleration due to gravity is bigger, but the period is a fraction with the denominator having that G. So as G gets bigger, the overall fraction gets smaller. So we could say that the period of the pendulum is greater on Earth. We're dividing by a smaller number when we calculate for Earth, So we're going to be getting an overall larger answer than for Jupiter. So there we go. Let's go to number 12. And again, if you have questions, don't be a stranger. All righty. Oh, I need to bring back the cursor. All right. Number 12. Looks like we have horizontal position and time as a graph here. And it reads, a block on a horizontal surface is attached to a horizontal spring of negligible mass and a spring constant of 30 newtons per meter. The other end of the spring is attached to a wall and there's negligible friction between the block and the horizontal surface. The block spring system experiences simple harmonic motion as shown in the graph. What is the change in the spring potential energy of the block spring system from when the block is released to when the speed is greatest, or to when it has the greatest speed? Let's go ahead and see what we're thinking here. Mhm. Okay, we'll go ahead and call it here. So when is the speed going to be the greatest? Well, we have to be careful here because we have learned that speed is going to be the graph or the slope of a position time graph. And so if we notice, our speed is going to be greatest right around here, which happens to coincide with the equilibrium point because that's when we have zero position from equilibrium. So if we look at this, they want the change in the spring potential energy. That means that they want the final spring potential energy minus the original spring potential energy. And let me change these here. It's going to be US for spring, and then that's final minus original. That's going to be the change in spring potential energy. So let's find out how much spring potential energy we have. Well, it's going to be 1/2 K times, well, the position is zero. Really, the displacement is zero. Zero squared. We really should be thinking the stretched length. But as far as we can tell, this is the equilibrium. We have not stretched or compressed the spring when we are at a position of zero. Minus 1/2 the spring constant, which is 30 newtons per meter. I'll just do that. And what is the displacement? Well, it has been pulled 4 meters, and they're technically negative, but when we square that, that won't really matter. And so this becomes 0 minus 4 squared is 16. Half of that is 8. 8 and 3 is 24. And then we add a 0. Newtons per meter times meter squared. One of those meters cancel out. We get Newton meters. So this is dimensionally correct. We get the units of energy, joules. And so C, 240 joules, is correct. Number 13, we got another graph. This time, the horizontal position is oscillating and changing from a value of 2.5 to 1.5. And it reads, a block of mass 0.4 kilograms on a horizontal surface is attached to a horizontal spring of negligible mass. The other end of the spring is attached to a wall, and there is negligible friction between the block and the horizontal surface. The block spring system then experiences simple harmonic motion, as described by the graph. And they ask, the maximum spring potential energy of the block spring system is most nearly. Greenland Poland. I like this question. Because it's hard, it's challenging. Anything worth doing is worth doing right and taking the hard path. Okay. Birth by fire, as I used to say at the beginning of class. I'll give us about another 10 seconds. This one requires a fair bit of calculation. All right, so let's go ahead and take a look at this. So as we saw, the spring potential energy is going to be given by 1/2 K times delta X squared, where this is the displacement from equilibrium. So there's a potential mistake that you can make right away. Because if you don't read this graph correctly, you're going to get the wrong displacement from equilibrium. Our equilibrium, or our graph, is centered around 2 meters, which means that at most, our displacement is actually 0.5 meters. So be careful with that. And someone rage quits now. Just kidding. I'm assuming they have to leave. Okay, dinner is calling. Very nice. Enjoy the review. Enjoy dinner. So that's the first part. The next part is, well, what the heck? They didn't give us the spring constant. They gave it to us last time. This is where you have to get resourceful, because the period of oscillation, we go there all the way over to Mordor, and then we come back to the Shire. And so our period of oscillation here is 3 seconds. And we know that the period of a pendulum is 2 pi square root of m over k. So we go ahead and do this. We get t squared is 4 pi squared m over k. And now we can get our spring constant. The spring constant, we're just swapping these two bad boys right here. We multiply by k, and then we divide by t squared. Basically, as I like to say, they swap spots, and we get 4 pi squared m all over t squared. And I just went ahead and distributed that over bar across the whole expression. So let's go ahead and plug in some numbers. So this becomes 4 pi squared, those are just numbers, times the mass, which is 0.4, all over 9. And so here's our spring constant. Hell, well, we can go ahead and plug all this in over here. And we finally get our spring potential energy here is going to be 1/2. Now, just to kind of maybe avoid potential mistakes, let's go ahead and evaluate this. Pi squared is approximately 10. So we have 0.4 times 10. This is going to become approximately 4. 4 times 4 is 16. This is going to be 16 over 9. So we're going to go ahead and plug that in here just like that. We're not going to evaluate it. I think that becomes like 0.666666. No, 1 point, because it's 2/3. Yeah, 1.66666. Sorry. And then the displacement of 0.5 meters quantity squared. You do your hokey pokey, and what you find out is our answer here is 0.2 joules. This is 0.25 or a quarter and a half multiplied gives us an eighth. The 8 cancels that, and you get 2 over 9-ish approximately. And that's going to be about 0.2. 0.22222. How did you get? Oh, so very important. How did we get the displacement? Remember, the displacement for, like, if we look at this, our motion is centered around 2 meters. And so this is the equilibrium position. And so this is when the spring feels no force. If I let go of this mass at the 2 meter mark, the spring is neither stretched nor compressed, which means that there is no force pulling on this block. The forces would be balanced. That's why we call it the equilibrium point. And we only begin to store energy if we pull it from that position. And so if we look at the bounds for our graph, it's going to be having a maximum position of 2.5 and a minimum position of 1.5. And so that gives us a displacement of 0.5 meter from 2 in each direction. So yeah, that's the big gotcha here. A lot of people would plug in 2 to their answer, and if you multiply by 2, that's a factor of 4 bigger. So you're going to get maybe about 10 times bigger. And so depending on how you calculated some things, you might get B or C. Because if you multiply by 4, you get about 0.8. A little off topic, but when we go into the exam on Wednesday, how many questions do you recommend for us to get at least a 4? Every single one of them. Nah. So because the multiple choice and the free response are combined together, it's a little harder. Some people are better at free response or multiple choice. Generally speaking, you want to be able to get about half of them correct. If you get about half of them correct, you're looking at a 4. If you get about 3/4 of them correct, you're at a 5. Now, the free response you can help you pick up points where the multiple choice are all or nothing. So try to aim for at least half the points on the AP exam, and you'll be in a good spot between a 4 and a 5. That's kind of like, if you remember my silly curve, 41% gave you a C for my curve. That's a 70. That's passing. That's a 3 on the AP exam. 57% around there, depending on the exam, is about a 4. And then 71% is about a 5 or a 90 on my test. All righty. Here we have another spring mass system, and they define the coordinate system for 0 position to be at what appears to be the equilibrium. And this bad boy is going to oscillate between a negative 0.3 meters and positive 0.3 meters. And they give us a graph of the kinetic energy, which as soon as we see this, we should be thinking, well, it should be going the fastest at a position of 0 meters because it was accelerating up until that point, and then the spring no longer exerts a force. So that's the peak of its velocity because it has stopped accelerating. And that's coincidental, or that coincides, with the graph. So it looks like we're good. It reads, a block on a horizontal surface is attached to a horizontal spring of negligible mass and spring constant K. The other end of the spring is attached to a wall, and when the spring is unstretched, the block is located at a position of x equals 0 meters, as shown in figure 1. The block is then pulled to a position of x equals 3 meters and released from rest so that the spring block system oscillates between a position of x equals negative 0.3 and a position of x equals 0.3. A student creates the graph shown in figure 2, which shows the kinetic energy of the block spring system as a function of the block's position. Which of the following mathematical routines can a student use, if at all, to determine the approximate change in the spring potential energy of the spring block system when the block is moved from a position of x equals 4 to a position of x equals 0.02? Another thing, you do not get penalized for incorrect answers on the AP exam. So don't leave any questions unanswered, okay? Hesitation is defeat. If you find you're running out of time, screw it. Letter of the day if you want, randomly choose. Don't mind game yourself and put C for everything. You need to do like 10,000 questions before you pick up 3 C's randomly more than any other letter. So you might as well just guess willy-nilly. But you can almost always eliminate 2 answer choices. All right, let's see what we're thinking. All righty, we'll go ahead and call it here. Because friction is negligible, and let me just make sure. Do they actually tell us that that friction is negligible? Yes, okay. No, the mass. Okay. So we have to be careful here. They don't tell us it's frictionless unless someone here can tell me that they do see it. But let's go ahead and see here if these make sense. So they want us to find the change in spring potential energy from when it goes from for when the block goes from a position of 0 to 0.2. Now, if energy is conserved, we can take the original kinetic energy plus the original spring potential energy and set it equal to the final kinetic energy and the final spring potential energy. And we can find their changes. If I move this guy over and then move this guy over, we get the kinetic energy minus the final kinetic energy is going to equal the final spring potential energy minus the original spring potential energy. So we have to be careful. There's a trade-off. And we want to find the change in spring potential energy. That's going to be delta U spring. And if we look here, that's going to be the kinetic energy at the beginning minus the kinetic energy at the end. And that's because there's a negative. So let's see here. So if we look at this, we're starting at a position of 4. Let's see here. Subtract the kinetic energy of the block at this from the kinetic energy of this. And it looks to me like answer choice A is our best answer, because we're going to take this and subtract it from that. Now, because they did not tell us that friction is negligible, I would be a little wary and think D is a good answer choice. Let me check what the College Board here is thinking, because this one feels like a gotcha. Yeah, no. The answer choice is A. Okay. Yeah, no, we can actually find it. I just really don't like, because even their wording, look at their wording. It's like, okay. It's like the College Board cannot leave this to interpretation, in my opinion. I think this is a poorly written question, or not poorly written question, but because we've been told to not assume friction is negligible unless explicitly told so. Oh, you're going to leave now? Okay, have a good one. Enjoy. No problem. Since I am recording this, we should have that video up later tonight. Because here they say the mechanical energy of the system should remain the same. Like, how dare you? Like, we need you to tell us this. We can't make that assumption right away. Here, because this answer fits really well with what we said, we can go ahead and go with answer choice A. But I could see where D might be, a tantalizing option. Kind of like if we're talking about potential energy, if they just name the block but not the spring or the earth, that object has no potential energy. And so that's a very important technicality that they love to stress. So if they don't say that, automatically you should be wary and say, okay, I cannot include spring or gravitational potential energy. And then when they review the exam, some teacher's going to be like, yo, you made a mistake. And then they'll fix it. But in that moment, it doesn't feel good. So anyways, off my soapbox. Yeah, exactly. I thank you for mentioning that. That's what my reasoning here was. If we notice, this graph is beautifully symmetric. And now I'd be careful. It's not exactly an arc. It's a sine squared graph or whatever. But even that, there should be an inflection here, and they don't even include that. So, but if we notice this is symmetric, we go the same distance in both directions, and we have the same kinetic energy at these points that are, equidistant from the position, the equilibrium position. So I would say that, yeah, we can say energy is conserved. Very good point. If this graph here, for whatever reason, were skewed, something like this, I got a little carried away there. So if it was skewed like this, here, this would be a perfect evidence that, hey, we did not oscillate to equal amounts of amplitude on both sides. This is not simple harmonic motion. We do not have energy being conserved. Because really, I need to have zero kinetic energy at this point. I need to stop at my apex. And if my apex of my motion is different from the left to the right, then we can definitely assume energy is being lost. Very good point. All right, here's the same kind of scenario, except they give us a bit of information. So, just what we were talking about. So here we have a graph of the predicted kinetic energy. Feast your eyes on that. And then we happen to have the actual kinetic energy graph. So this guy is not maybe centered, but we'll have to see here the extent of the oscillation. Okay, so let's go ahead and see here what they tell us. A block on a horizontal surface is attached to a horizontal spring of constant 50 newtons per meter. The other end of the spring is attached to a wall, and the block is initially at the equilibrium position of the block spring system, as shown in the figure. The block is moved to a position of 60 centimeters and released from rest so that the system oscillates. A student predicts that the kinetic energy of the block spring system as a function of the block's horizontal position is shown in graph 1. When the experiment is conducted, the block does not make a complete oscillation because frictional forces were not considered in the student's prediction. Data is collected about the actual kinetic energy of the block spring system as a function of horizontal position and is used to create graph 2. How can the student use one or both graphs to determine how much mechanical energy is converted to non-mechanical energy from the instant the block is released from rest to the instant when the block is no longer in motion? This is a mouthful. So we want to find out how much mechanical energy was lost due to friction. And so here, hopefully you're following on the AP Classroom because it's going to be hard to see everything here. All righty, we'll go ahead and call it here. So the idea is, because there's going to be transitions in potential and kinetic energy, we really want to compare maxes and minimums. So for instance, we know that we should have 0 joules of kinetic energy when we release it from rest. Now, if we compare the predicted kinetic energy at position 0, what this tells us is that if energy was conserved, 9 joules was the starting point of our spring potential energy. So it's going to be 9 joules at 60 meters, or 60 centimeters, sorry. And it's going to be perfectly converted into kinetic energy, and we would have 9 joules of kinetic energy at this 0 centimeter mark. That's the case here. What we notice is that when we reach our maximum kinetic energy here, we really have about 5 joules of kinetic energy. So let's go ahead and see here. So what does this tell us? So we can go ahead and use the graph 2 to determine the spring potential energy stored at the instant that the block is no longer in motion. Because when we are at 30 centimeters, in reality, at 30 centimeters, we should have about 7-ish joules still left of energy. So at this point, we know how much spring potential energy we have here. This is really 7 joules. When in reality, when we come to a stop, we should have 0 kinetic energy. So we're deficient 7 joules, basically. Or sorry, we're deficient 2 joules. And so C is going to be the best way to do this. Subtract this value from the maximum predicted kinetic energy of the block so that we can go ahead and get that. Because what we find out is that here we should have had 7 joules of kinetic energy and 2 joules of spring potential energy. In reality, we have 0 joules of kinetic energy. Sorry, this would be 2. We have 0 joules of kinetic energy because we've stopped. But when we're at that position, we should have 2 joules of spring potential energy. And so because the spring potential energy only depends on position, we can get that and know that whenever we're 30 centimeters off to the side, that's how much potential energy we have in our spring. We should have really 7 kinetic joules of kinetic energy, but we don't. And so we're short 7 joules. Let's go to 16. Student Y is at rest while sitting on a swing. Student X stands behind student Y and provides an initial applied force to student Y. Student Y's position on the swing then oscillates. Which of the following claims is correct about student Y? All righty, we'll go ahead and call it here. So if we look at answer choice X, it reads, if student X applies a greater force on student Y, the period of oscillation will decrease compared to the original situation. Very important. Student Y is behaving like a pendulum, and the period of oscillation for a pendulum just depends, it's proportional to square root of L over G. This external push is not going to change the time it takes us to swing. Sure, she's going to go faster, but because she goes faster, she has more kinetic energy to trade off, and so she's going to go higher off in her swing. So not going to be the case. And so both of these, period and frequency, are inverses of each other. If the period does not change based off of this push, then neither will the frequency. She's just going to go through a bigger arc, but she's going to take the same amount of time. That's the crazy thing about simple harmonic motion. If you have a small amplitude, you'll move slower, and it'll take the same amount of time if you have a big amplitude. You'll just move faster to cover up that, because your force is proportional to the displacement. If student X applies a greater force on student Y, the total mechanical energy of the student Y Earth system will increase compared to the, this sounds true. Here, they're defining the system as just the student and the Earth. So when this guy pushes, that's an external force. And so they're going to do work on the system, increasing or changing the mechanical energy of the system. So I think C is pretty good. Let's go ahead and look at D. If student X applies a greater force, the maximum gravitational potential energy of the student Y Earth system will be the same as the original. No, they're going to go higher. It's not going to be the same as before. So C is their best answer choice. Let's go ahead and look at the next question. And let me know if we have any questions. 2 C's in a row scary. Hey, that's just statistically, like, they're gonna, dude, I've had some exams, and these are like official exams, where like you get strings of letters. Sometimes it's been like 3 A's or 4 B's, and it just feels weird. And you just have to know for sure, like, okay, is this correct or not? Like, and don't psych yourself out because of it. In this case, yeah, it just worked out that way. 2 C's in a row. I think a lot of times exams are designed to not try to do that, to avoid students like mind gaming themselves. But maybe next year in physics 2 and 1, I'll do like an all C test except 1. That's terrible. All right, let's go. A block of mass M on a horizontal surface is attached to a horizontal spring of negligible mass with a spring constant of 20 newtons per meter. The other end of the spring is attached to a wall, and there is negligible friction between the block and the horizontal surface. Nice. When the block is pulled to a position beyond the spring's natural length and released from rest, the block experiences simple harmonic motion, as expected. A graph of the force exerted on the spring as a function of the block's position is shown. What is the spring potential energy stored in the block spring system at position B? And let me make sure this is not a multiple correct. Yeah, no, it should not be. This is only one correct. All right, we'll go ahead and call it here. This one's a little weird. It's like, what the heck? They don't give us enough information because what is this position, right? So let's go ahead and see here. We know that the force is 10, or sorry, this is going to be about, let's see here if we can get one that's nice and even on the graph. Okay. So we are told that we have a spring constant of 20 newtons per meter. So let's go ahead and see here when we have a force of 5. So F equals K times delta X from equilibrium. And so we're going to have 5 over 20. That's going to give us 1/4 0.25 meters. So we know that this distance here is 0.25 meters. So let's try doing that over here. Well, shoot. This is almost 5, but it's a little short. I think maybe, just maybe, it's going to be about 0.2. But let's just try and do this for about, let's see here. This would be 2.5. Yeah, it's going to be about 4. So the force here is going to be 4 newtons. The spring constant is 20. So we're going to go ahead and say the displacement here is about 4 over 20 newtons, and then newtons per meter. The meters go to the top because we're dividing by a fraction. And we get 1/5 of a meter, or approximately 0.2 meters. Then we can go and say, well, the spring is 1/2 K, 20 newtons per meter, times the displacement of 0.2 meters, quantity squared. This becomes 10 times 0.2, which is 0.04 when we square it. Then 20 came from 20 divided by 2, and so about 0.4 joules. So B is our best answer choice. Let's go over number 18. A student attaches a block to a vertical spring so that the block spring system will oscillate in simple harmonic. Yeah. Which of the following explanations is correct about why the system oscillates in a simple harmonic motion about the system's equilibrium position? So this one's just asking, do you remember definitions for why we experience, or causes for spring potential, or sorry, simple harmonic motion? I'm all over the place, sorry. Where's my poll? Whew, sorry. All righty, we'll go ahead and call it here. Let's go. Okay, so we have seen that for simple harmonic motion, that occurs when the force is proportional to the displacement. And because the force is proportional to the acceleration and the mass, we can say that the acceleration is going to be proportional to the displacement. So velocity is proportional, probably not. Acceleration is directly proportional to and opposite in the direction of the block's displacement. B looks really good. Let's go ahead and see the other ones. The block's acceleration is directly proportional and opposite to the direction of the block's velocity. No. And then because the net force exerted on the block is directly proportional to and opposite the direction of the block's acceleration. No. Really important. An acceleration can never be in an opposite direction of the net force. The net force gives us that acceleration. They will have the same direction because mass is a non-vector. It's a scalar or scalar. All right, go to 19. We have a 50 Newton per meter spring. Equilibrium point is 0. The maximum extents are 1/2 meter in each direction. And they give us a free body diagram. A block of 0.5 kilograms of mass is on a horizontal surface and is attached to a horizontal spring of negligible mass and spring constant 50 newtons per meter. The other end of this, this part, the friction is negligible. When the spring is stretched, is unstretched, it is located at a position of x equals, okay? And then it is pulled to this and released so that it oscillates, All these questions kind of seem really repetitive, so I'm kind of skipping them, sorry. But the whole, we release it from rest from a position that is not the system's equilibrium position so that it undergoes simple harmonic motion. It's kind of what they all say there. A free body diagram at a particular location is shown. Based on the free body diagram, at which of the following locations could the block be? Excuse me, sorry. As you guys saw, I was up late doing grades. Oh no, my mouse is about to die. All right, we'll go ahead and end pulling here. So what's the idea? We know that the spring force is 8 newtons. So we have the force in the spring is negative K times delta X. We can get the spring force and divide it by the spring constant to get the displacement. And this is going to be 8 over 50. And so you can go ahead and type that in here. That's not a nice clean number. I'm trying to estimate it actually. 54 is the sixth. So about 0.15? No. 8, enter 50, divide. 0.16 actually, smack dab. I should have not hesitated there. Okay, so it is at a position or a displacement of about 0.16. So let's see here. Ooh, is this a multiple correct? Because it looks like it's going to be one of these two. Now let's go ahead and look at the arrow for the spring force, because that's what's going to really tell us where it's at. Well, if I have a spring force pulling me to the left, that means that I'm over here. I have stretched and displaced myself to the right so that we can go ahead and say that it is at a position C between 0 and 0.5 meters. There we go. We didn't even need the actual number. We just need to know where we at. We are on the right side over here because the force is this way. If I'm on the left side of the equilibrium position, the spring pulls to the right. And so we should have seen negative. Well, bad. Okay. And really the spring force here is a negative 8. So negative 8 divided by the negative.
Mr. Gasta, wait, I think you just did. So it's positive 0.16?
Yeah, if we do the little negatives here, the force points to the left, so that's a negative 8 newtons, and then you divide the negative over with a 50 if you want, and then that turns it into positive. That's another way to justify this numerically. What I would have done is looked at the arrow and recognized if the spring is pulling me to the left, I'm going to have a position that is to the right of the equilibrium point. Oh, enjoy your dinner. Did that answer your question?
Yes, thank you.
All right, let's go ahead and look at number 20. So, oops, let's go ahead and scroll over to the side. A block of mass M hangs at rest from the bottom of a stationary spring that stretches to a distance A from the spring's unstretched length. The block is then pulled an additional distance A so that the string is stretched a total distance of 2A as shown in the figure. The block is then released from rest and the center of mass of the block vertically oscillates at a displacement of 2A from its lowest position to its highest position. The lowest vertical position of the block's center of mass is located is the location at which gravitational potential energy of the block spring Earth system is 0. So we know that UG is going to be 0 here. Which two of the following claims are correct about the mechanical energy of the system? We're going to select 2 answer choices. So very important. On the AP exam, you must choose the 2 correct answers to get it correct. If not, it is incorrect. So just kind of keep that in mind. And those will be the last 5 questions on the multiple choice. So just be mindful that if you reach the last 5, you should be answering 2 or providing 2 answers. Alrighty. So let's go ahead and call it here. So the first thing we should know is that when we have no stretch in our spring, when it is completely unstretched, we have the maximum amount of kinetic energy. Sorry, when we're at the equilibrium position, my bad. When we're at the equilibrium position, which is defined by A, which is when we hang it is different than if this block were horizontal. In a horizontal position orientation, the equilibrium position is the unstretched length. But when we do this here and we hang it vertically, this is the equilibrium point because the force from the spring is going to be balanced by the force due to gravity. So here, this is where the net force is 0. So the acceleration is 0. We're going to be accelerating until we get to that point in both directions. So B is one of our answer choices. The kinetic energy is at a maximum when the string is stretched a distance a from its unstretched length. The other one is C. The potential energy of the system is maximum when the spring is stretched a distance 2a from its unstretched length. Okay, so here they're talking about U potential and U spring, or sorry, U. Oh my God, I am actually starting to get tired because I am mixing things up real bad. It's going to be the sum of gravitational and spring potential energy, such that if this guy oscillates a distance a away, even though the gravitational potential energy here is 0, we have stretched all of that spring potential, or that spring creating spring potential energy. And even though G is 0, as this guy gains gravitational potential energy, UG is proportional to the height, which is going to be essentially the distance A. Whereas spring potential energy is changing and it's in proportion to h squared or a squared. So as we climb up, even though we gain gravitational potential energy, we are going to be losing more spring potential energy per se because of this distance squared factor. Such that what we find out is that even though at this point we're going to have the maximum amount of gravitational potential energy, the spring is basically having no energy stored in it, and so it's not going to matter. And our kinetic energy is essentially 0. So C is our best answer choice here. Let's go to 21. I know, it's already like 7:05, sorry, and we still have 6 questions after this one, these two. A student attaches a block to a vertical spring so that the block spring system will oscillate if the block spring system is released from rest at a vertical position that is not the system's equilibrium position. Which of the following measuring tools, when used together, can be used to determine the spring constant of the spring? Select 2 answer choices. All right, we'll go ahead and call it here. So we can get K if we know the force and we divide it by the displacement. So maybe we're thinking, hey, let's measure the displacement and measure the force, and all of a sudden, oh no, we have no way of measuring the force. So this approach is not going to work. But we also know that the spring potential, the period of a spring is given by 2 pi square root of m over k. If we can measure the mass and the time of oscillation, we can get k. So electronic gives us mass. The stopwatch gives us the period of oscillation. If we're thinking the spring potential energy, 1/2 k times delta x squared. As far as we know, we don't know how to measure this. At best, we can go ahead and translate that all into kinetic, but we would still need the velocity and the mass, which is going to require too many variables. We're going to need to measure displacements. We're going to need to measure masses. And we're going to need to measure velocities, which require positions and times. And so we're going to measure positions and time. Well, we might as well just measure time and the mass. So, well, bam, there we go. Least amount of materials. Let's go to the last one here for this part. A block of mass M is on a horizontal surface that is attached to a horizontal spring of negligible mass. The other end of the spring is attached to a wall, and there is negligible friction between the block and the horizontal surface, and the block is set into simple harmonic motion. A graph of the force exerted on the spring as a function of the block's position is shown. A student collects data such that the force that the spring exerts on the block for every 0.25 seconds is plotted on the graph as shown. The block has and so which of two of the following claims is correct about the block spring system during the time in which the data is collected? Okay, we'll go ahead and call it here. So let's go ahead and see and visualize what's going on. Here they're giving us of the force as a function of time. And we have seen that the maximum amount of force is at the extremes of the motion. The net force here is 0 at the equilibrium position. And we're going to be going the fastest at the equilibrium position. And we're going to stop at the extent of our motion, at the apex. And this is where the force is going to be maximum. Because if this is our displacement, our force is proportional to the displacement. So let's go ahead and see here. The block has maximum acceleration at 0.5 n, where n is a whole number. Well, we have a large amount of force here, here, 0.1, okay. Here, and here. So A looks very good because the acceleration is really just the force divided by the mass. And if this guy is max, then this guy will be a maximum value. So answer choice A. Now, if we look at this, the block has a maximum speed at 0.5 n times letter choice C. If we notice, when the force is maximum, the block stops. So if anything, that is not true. The speed is 0, if anything, at 0.5 n. And then by that virtue, because the momentum is speed with a direction times the mass, velocity times mass, this will also be 0. This will be incorrect. The momentum is 0 at these points. So B is our best answer choice. The block has maximum spring potential energy at all times where 0.5 at 0.5 n. And so that's because we have the most amount of displacement. And so what we find out is that when delta x is maximum, the force from the spring is maximum, and the spring potential energy is a maximum. All right. So that's technically it, but we still have the first 6 questions to go. If you're like, if you guys want to stay, I'll be recording these anyways. And so other than that, have a good one. I do plan on meeting tomorrow, just one last study before the AP exam, or just answer y'all's questions. So in experiment 1, so we have 2 experiments. It reads, in experiment 1, a block of mass M is attached to the end of a vertical spring, a spring constant K naught. And its free end is at a vertical position of L original, as shown in figure 1. No problem. Have a good one. As shown in figure 1. The mass of the spring is considered to be negligible. When the block is attached to the spring and is at rest, at the block's equilibrium position, the spring is stretched so that its end is at a new position L1. So here it is showing that we're going to pull it a distance L1. No problem. Keep it easy. As shown in figure 2. The block is then pulled down to a new vertical position L2 and is released from rest so that the block spring system oscillates. Assume that the reference line for zero gravitational potential energy is at the lowest point of the system's vertical displacement from equilibrium. The experiment is assumed to be performed near Earth's surface. And the question is, what is the magnitude of the change in potential energy of the block spring system? So if you notice here, they do not mention the Earth. Do not worry about gravitational potential energy as it travels from its lowest position to its highest vertical position. So let's go ahead and see here. When it is at the lowest vertical position, we have stretched the spring. A total displacement, the displacement to the bottom is going to be L1 plus L2. As this guy oscillates, the displacement to the peak or to the top is going to be L1 minus L2. If I stretch a spring so that it oscillates, if I stretch at a distance L2 down, it's going to oscillate from there a distance L2 up. Such that the amplitude of this is always going to be L2. They don't give us any numbers, but we can go ahead and use this. And they want us to find the change in potential energy. So they're going to want delta U equals U final, U spring final, minus U spring original. Excuse me, sorry. And it's going to travel from the lowest point, so this is the original position, to the highest point. That's the final position. So this is the final position. This is the original position. Well, what do we do from this? Well, we know that the spring potential energy is given by 1/2 K times delta X squared. So we're going to need to use that. So the original spring potential energy is going to be 1/2 K. And the displacement to the bottom, this is the original displacement, is L1 plus L2 quantity squared. And the final spring potential energy is going to be 1/2 K L1 minus L2 squared. Now we notice none of these equations actually fit it. This is the closest that they give us, and that's the gotcha. This is just the original spring potential energy. We need to get the change. So this is where we got to get a little sweaty with our algebra and expand this quadratic. This becomes 1/2 K L1 squared, and then plus 2 L1 L2. We're just foiling this. Plus L2 squared. If you have trouble foiling, I mean, hopefully you got an Inspire, but kind of assume by now that's you know, like something that you know how to do. It's just the first term squared plus the product of the intermediate terms doubled, and then plus the final term squared. Here we have a negative, so we have to be careful. It's going to be L1 quantity squared minus 2 L1 L2, and then the negative L2 gets squared, so that becomes positive L2 quantity squared. So what do we do with this? Well, we need to subtract them, final minus original. So we're going to have a 1/2 K. We're not going to worry about that. We'll just write that here, 1/2 K. And then we're going to put the brackets. The final term here is going to be L1 squared minus 2 L1 L2 minus L2 squared, sorry, plus minus L1 squared plus 2 L1 L2 plus L2 quantity squared. This one is nasty. This is a lot of math. So what do we find out? Well, if we distribute our negative, what happens? We're going to get L1 minus L1 squared. Those guys cancel. We have a plus L2 squared minus L2 squared. These guys are also going to cancel. And so what's going to remain out of all this is 1/2 K negative 2L1 L2 minus 2L1 L2. And we can clean this up. This is 1/2 K. This becomes 4. Negative 2 minus 2 is 4L1 L2. And lastly, these guys cancel for a factor of 2KL1 L2. And so this is a lot of work, but C is our best answer choice here.
Mr. Gasca, in that previous question, how is L, I think it was top, like how is it L1 minus L2? I don't understand how you got that.
Okay, so that's kind of like a tricky bit. So, well, if we had done experiments in labs, what we would have found out is that, let's say I happen to have something at my equilibrium position, which is a distance L1 from the unstretched length. If I pulled this guy down 3 centimeters, it's going to oscillate between, it's going to oscillate downward 3 centimeters, and it's going to go up 3 centimeters. So let's say L1 was, I don't know, 10 centimeters. Then if I happen to pull my mass 3 centimeters from the bottom, then this distance here would be 13, or L1 plus L2. And when it goes all the way to the top, what we will find out is that it's going to stop at a distance of 7 centimeters, or L1 minus L2. So we're going to, our equilibrium position is L1, and we're going to be oscillating about a distance L2 from there. And so when we go all the way to the bottom, we add it because it makes more stretch. When it swings up, we subtract by L2 because it stretches the spring less. And that's just a neat thing about simple harmonic motion. The amplitude in one direction equals the amplitude in the other. And so it's like symmetric. And I don't know if that answered your question, but it's just kind of like a, sorry, it just works out this way because of energy transformations. If I happen to have my spring mass system there at 10 centimeters, and if I were to lift it 3 centimeters and let go of it, it would oscillate and it would fall until it reached a distance of 13 centimeters or 3 centimeters below. And then it would go back up 3 centimeters above equilibrium and then oscillate back down 3 centimeters below the equilibrium. And so I think that answered the question, but if not, let me know. We'll go ahead and continue to the next one. So they tell us that the students conduct experiment 2, in which the same block is connected to the same spring on a horizontal surface. The spring is stretched a distance L2 beyond its natural length and released from rest, allowing the block spring system to oscillate. Frictional forces are now considered to be negligible. Which of the following claims is correct about how the period of oscillation for the block spring system in experiment 2 compares to the period of oscillation for the system in experiment 1, and what evidence supports this claim? So if we notice, it's still the same spring. And so whether we stretch it horizontally or vertically, that doesn't matter. The spring has no mass. So K is constant, the mass is the same as before. So what we find out is that the period of oscillations are going to be the same because both the block and the spring are used in both experiments and they are identical. So again, let me know if we have questions over that one, but it seems kind of weird. And here we just have to remember the principles, which is that the amplitude of displacement does not change the period. What about delta x? So really important, the period of oscillation does not care about the amplitude. It just cares about the spring constant and the mass. If we stretch it further, it'll move faster, but it's going to move through a larger path, and those two effects will cancel each other out. So the displacement really has nothing to do with the period of oscillation, especially for a spring mass system, as long as it doesn't reach the elastic limit. So it's kind of like a gotcha here. Let me know if that answered the question. I'm going to go ahead and proceed. If you have another one, feel free to ask. In experiment 1, a block of mass big M is attached to the end of a vertical spring of constant K naught. The spring end at a vertical position of L naught, as shown in figure 1. The mass of the spring is considered to be negligible. When the block is attached to the spring and is at rest, it is at a position L1 as shown in figure 2. It is pulled down to a new vertical position L2 as shown in the figure and released from rest so that the system oscillates. Assume that the reference line for zero gravitational potential energy is at the lowest point in the system's vertical displacement from equilibrium is 0. The experiment is assumed to be performed near Earth's surface, and the question is, a student is asked to perform experiment 1, but with a spring of an unknown constant. The student performs 4 trials of the experiment with blocks of different mass and collects the data that are shown in the table. How should the student graphically analyze the data in order to determine the spring constant of the spring? So let's see here. We are changing the mass. We're getting different periods of oscillation. So if we look at this, the period of oscillation for a spring mass system, as we've been saying, is given by 2 pi square root of m over k. And we have the period and we have the mass. So generally looking at this, they're talking about creating a graph. So we should be thinking, well, how are we going to graph this? How are we going to linearize this? Because usually we want to work with the slope to approach some sense of the y equals mx plus b. So let's go ahead and see here. Well, we can make t our y variable. Now we have to be careful. We're looking for k. So we cannot have k as part of our independent variable. So we can kind of clean this equation up and say it is given by 2 pi square root of m over square root of k. This is our unknown, but we can make this quantity here behave like x. And what will result in that, or what the result of that is that the slope would be 2 pi divided by square root of k. So create a graph of the period of oscillation plotted on the vertical axis, okay? And the square root of mass of the block plotted on the horizontal axis. B looks to be our best bet, answer choice, or our best bet. Use the slope of the best fit line to determine the spring constant, okay? Here they're saying the mass, and then this is the square of the mass. Very important. We look at the exponents. Because it's a square root of m, what we want to recognize is that the period is proportional to square root of m. But we want to plot this as y. We want to plot this as x. Go to question 4. A block on a horizontal surface is attached to a horizontal spring of negligible mass as shown in figure 1. The end of the spring is attached to a wall and there is negligible friction between the block and the horizontal surface. A group of students want to investigate how stretching the spring, oops, sorry, just saw the chat. Oh, what about the square root of 2 pi? Let me know what you mean by that, but because it's all a constant, that's just going to be like, for instance, let's say we found out that the slope in this case, for whatever reason, let's say the slope was equal to 10 units of whatever. It would be seconds per square root of kilograms. Well, we can go ahead and set that 10 equal to 2 pi over square root of k. And we can rearrange this and get square root of k equals 2 pi all over 10. So the 2 pi doesn't really matter. It's just part of like a multiplier. So we can go ahead and say that K is really going to be 2 pi quantity squared all over 10 quantity squared, and it works out. Okay. All righty, let's go ahead and go to the next one. And so let's see here. In a trial, for each trial of the experiment, the spring is stretched a variable distance delta x from its natural length as shown in figure 2. And blocks of different mass may be used. The block is released from rest and the system is allowed to oscillate. Figure 3 shows the horizontal position of the block as a function of time for one trial of the experiment. The students must conduct an experiment to determine the magnitude of the force exerted on the block when the block is at a position of A over 2, where A is the amplitude of oscillation for the block spring system. For each trial, the students attach blocks of different mass m to the spring and stretch the spring a known distance A, release from rest and measure the period of oscillation, and then measure the maximum velocity of the system. How should students use a graph to determine the magnitude of the force under consideration? So this one's kind of messed up. This is kind of complicated. They're giving you all sorts of information. It's kind of hard to sort it out. But the thing we want to do is determine the magnitude of the force on the block when it is at a position of this. And they're varying the mass. So if we've seen this, we're varying m. Kind of like in the graph below, or I'm sorry, in the question above, we've seen that t is proportional to square root of m. So we know the time and we know the velocity. So what we can go ahead and do is we can go ahead and if we square this, t squared is going to give us m. Now the force in the spring is given by k times delta x. And they just really want the force. So the force in the spring here is going to be equal to m times a. And we know the mass. So the idea here is that we can go ahead and work with t squared because t squared is going to give us mass. And so we get t squared times a is going to give us the force in the spring. Now here, if we look at this, we're going to end up multiplying the result by delta x because this right here, one way we can think about it is really k. And so this one's kind of nasty, but I believe the best answer choice here is t squared as a function of m. V squared as a function of m is not going to give it to us. Best fit line t is not proportional to m, so we don't want to do that. And then the velocity is also not inversely proportional. So I don't think I did a very good job of explaining that one. But let's go ahead and see here what the idea is. But it's basically kind of what I was saying. Let me go ahead and type it in here. Oh man, this one's taking a while. Okay. And so therefore, so if we see here, therefore this relationship represents that the student should graph in order to determine the spring constant. The force exerted on the block is the spring from the spring can be determined by k times delta x. If the spring constant is determined, then it can be multiplied by the distance the spring is stretched. Oh yeah, so really quickly, I kind of like, this is where I kind of like didn't do a good job of explaining. So if we do t squared, that becomes 4 pi squared over k times m. So in this case, this is the slope. And just like I was saying before, here we can go ahead and get k by saying that it's going to be 4 pi squared over the slope. And so if we have k, then we multiply by the displacement, and there we go. All righty, number 5. In one experiment, the students allow the block to oscillate after stretching the spring a distance a. If the spring potential energy in the spring is U naught, then what is the changing kinetic energy of the block after it is released from rest and has traveled a distance of A over 2? Okay. And they want the changing kinetic energy. So that's going to be the final kinetic energy minus the original kinetic energy. Now we have to be careful. If we do energy conservation, we can set all of the energy before, the original spring potential energy plus the original kinetic energy equal to the final spring potential energy and the final kinetic energy. Now we're looking for the change in kinetic energy. So that means that we're going to want to move over K naught. And so over here we get K final minus K original is going to equal U spring potential energy at the beginning minus the spring potential energy at the end. And so this becomes 1/2 K times A squared, because it is at a stretched distance of A, minus 1/2 K. And then now we're at half that distance, but we have to be careful. Just because we are stretched to only half that distance does not mean that we have lost half of our energy. If anything, if we see here, and I've kind of written in a poor spot, so it looks messy, but this becomes 1/2 K A squared minus 1/2 K times A over 4, and this guy gets squared. So I have, and I wouldn't really worry about the halves, but I have a whole minus a fourth. That's 3 over 4 K A squared delta U times the 1/2. So it is going to be B.
So, Mr. Gaska, so when it's at distance A, it's at, that's like the beginning, that's where it was at rest?
Mhm.
Okay.
And we don't really have to find the kinetic energy. We don't have to set it equal to 0. They're just kind of asking for the change. So what I do is I write the law of conservation of energy. And really important, because this guy's not changing heights, we don't really need to worry about the gravitational potential energy exchanges in this case. And so I just rearrange this so I get final minus original for kinetic energy, because they're asking for the change in kinetic energy. If they were asking for the change in potential energy, then I would move the spring potential energy to the right side so that we would get the final spring potential energy minus the original. And then that would be the original kinetic energy minus the final kinetic energy if we were looking for delta U. And that was a question later on that was asked. But yeah, this is where it was at rest, but we don't really need to worry about that calculating the kinetic energies because we have position values. So we're better off finding the change in potential energy, because that change in potential energy, the negative of it technically, is going to be the change in kinetic energy. And let me know if that answered your question, if you have more questions or follow-up. So this question here reads, a block on a horizontal surface is attached to a spring of negligible mass as shown in figure 1. And it is allowed to oscillate. Okay, and a group of students want to investigate how stretching the spring within the spring system, within the block spring system, influences the motion of the system. Sorry, how stretching the spring. So they want to see that if we stretch it more, how does that influence the motion of the system? For each trial of an experiment, the spring is stretched a variable distance delta x from its natural length, as shown in figure 2. Let me just fix that. Okay. The block is then released from rest, and the system is allowed to oscillate. Figure 3 shows the horizontal position of the block as a function of time for one trial in the experiment. Which of the following, at which of the following times does the spring exert its maximum force on the block? And so we have horizontal position as a function of time. The important thing about harmonic motion is that the force is proportional to the displacement. And this is the equilibrium position. So we have maximum displacements at at 2 seconds, sorry, and at 6 seconds, and at 10 seconds. So because we have the maximum position or from the equilibrium point or the maximum displacement, we should be looking for one of these answer choices. And so 2 seconds is going to be our best bet. 4 and 8 are when we have 0 position. We are at the equilibrium position. There's no net force there, no force on the spring. All right, that should take care of that. Hopefully that made sense. If not, let me know. I'm actually going to delete this here, whoops, because it is skewing everything up. There we go. But I'll need to move this over now.
Mr. Gaska, I was gonna mention, I remember last time I asked, you said to remind you like close to like before the AP exam, I asked about the semester exam, like when it would be.
So the semester exam is going to be during our regularly scheduled time that we are set for semester exams. Now, what I'm thinking of doing, and I wouldn't like share this with everyone, but I'm thinking of, and as soon as I say this, really everyone's like being shared. I'm thinking that if people have shown up to these review sessions, I am going to exempt them from the exam. So it's one of those, I didn't want to make that announcement at the very beginning because I figured people would just show up, tune out, and then not pay attention and really kind of nullify the purpose for these reviews. But because I've seen some people, showing up for pretty much like every single session, it's like I want to, kind of recognize that extra time. You guys are going an hour and a half every other day here for physics.
Okay, that sounds good. Thank you.
No problem. Any other questions?
So with this last question, like with the 2 seconds and the maximum force on the or like so it says like the spring exerting the maximum force on the block, right? I was wondering, I realized now that the answer is pretty obvious, but what would the wording be if it was asking about like the potential energy? Like how would you ask that question except instead of kinetic energy, potential energy?
So for potential energy, we should also keep in mind that the spring potential energy is proportional to the displacement, but just the displacement squared. So recognizing when we are the furthest away from the equilibrium position, that is when we have maximum displacement and we're going to have maximum force, and potential energy is stored in the spring. And we kind of had a question where I made that note somewhere here. When the displacement is maximum, the spring force is maximum, and so is the potential energy. And they will be a minimum at the equilibrium position.
Okay. And also, I forgot what question which question it was specifically. I think it might have been something like this one, like similar, about finding potential energy, like finding spring potential energy by finding the maximum kinetic energy.
So I think that was this one here. And so here they're asking for what is the approximate change in spring potential energy. So again, we write out all the terms for the law of conservation of energy. And so, we're going to have kinetic and spring potential energies here. And because it's moving horizontally, we're not going to worry about gravitational potential energy. Now, because they are looking for the change in spring potential energy, that's delta U, or U final minus U original. So when I look at this equation, I find out, okay, I want to restructure this so that it looks like final minus original. I should have stopped recording when I made that announcement. Oh, well, if you're watching this video, let me know. Anyways, so here, because I have U final on the right-hand side, I am going to move the original spring potential energy to the right-hand side because that's going to require me to subtract it. So that's how we get this part here. Now, because I only want this to show up on one side of the equation, I need to move the final kinetic energy value to the other side. And that's going to give me K original minus K final, which is this part here. If you look at certain books or notes, they will tell you that the change in kinetic energy is equal to negative delta U, or delta U is equal to negative delta K. The thing about that is this one here doesn't really like help us out immediately. We would need to expand this and recognize, well, that's going to be the negative of the final kinetic energy minus the original kinetic energy. And then we distribute that negative over. And we get negative Kf plus Ko. And another way we can think about it is, well, then delta U is going to be, oops, I made a mistake. That's Kf. Ko minus Kf. So it's going to be the final kinetic energy subtracted from the original kinetic energy. And I don't know if that answered your question, but let me know.
Yeah, I think it did.
Okay.
Also, I talked to Daniel just before this, and he pointed me towards something on Reddit that was, and everybody on there is like saying it was a disaster.
Mhm.
So.
Yeah, I wanted to ask him. I saw he came in here, but he left. I'm assuming he was just kind of waiting, and we took forever. But I'm really curious to see what he thought about the test.
Yeah, he said that. Okay, he said that he expected
Let me
it
stop
to be
recording real quick.
fair.